Energy and Power, Lesson 2. Now, starter for Lesson 2, what is work? Now, hopefully we remember from last lesson, we said that work done is energy transferred. When a force moves an object, then work is done, and that work is equal to the amount of energy transferred. So in this lesson, when we look at kinetic and potential energy, we'll just be linking it to our ideas about work done. Some of these bits will be familiar from GCSE, especially the two formulas we're going to use. What we just need to be better at, compared to GCSE, is that language of of using the work done and energy transferred language. We'll also be thinking about conservation of energy. So our spec reference is still the same. On this bit of the spec, at the bottom, conservation of energy. So applying that principle of conservation of energy in the two formulas, mg delta h and a half mv squared, potential and kinetic energy, and looking at some examples. What do we need to be able to do? What happens when work done is what happens to the work done when an object is lifted? What are the energy changes taking place when an object falls? And what is the kinetic energy of the car if its speed is doubled? We're looking at those three things, aren't we? Work done, potential energy, and kinetic energy. If we consider an object that gains kinetic energy due to a constant force acting on it, it's initially at rest at speed 0 and then at a final speed v at time t. If we use the no-A equation, S is a half u plus v times t. That's going to simplify because u is 0, it starts at rest, to S is a half vt. Now what if we use the no-S equation? That equation is going to simplify too. It starts off as A equals V minus U divided by T, but U is 0, so we get A equals V divided by T. Now we're going to substitute that into Newton's second law. It's Newton's second law, F equals ma. A is V divided by T, so we get mv divided by T. So the work done is going to be force times distance. The force, mv divided by t, the distance from the top, a half vt. That's going to simplify because we've got t on the top and t on the bottom. They cancel, leaving us with a half mv squared. That formula looks familiar, doesn't it? Because our work done gives us the gain in kinetic energy. So we're saying that kinetic energy is a half mv squared, derived from the bits we've done so far, from two Suvat equations and Newton's second law. We just need to be careful for this. At A level, this formula only holds for speeds much less than the speed of light. If we get close to the speed of light, we need to use special relativity. We'll look at that towards the end of next year and look how this formula that we just derived, it's an approximation, and when we use a special relativity one, in most scenarios it becomes this formula. We don't need to worry about that for now, just as long as we're aware it only applies at low speeds, less than the speed of light. What if we're looking at potential energy? The energy of an object due to its position. If it's got mass m, if m is bigger, it's got more potential energy. If it's raised to a vertical height delta h, if that height is bigger, then the potential energy is bigger. Either way, the work done to raise it that high is the force times by the distance. The force is the weight of the object, mass times the gravitational field strength, and the distance is that vertical height delta h. So weight times height change, giving us mg delta h. Clearly, to get more potential energy, more mass, bigger height, stronger gravitational field. So like instead of Earth we could go to Jupiter and have a stronger gravity. We should note that that only holds for heights much less than the radius of the Earth. Why? That one we'll look at in September in our gravitational fields topic. But all we need to really think about is, as you get further away from Earth, the gravity does change. So when we look at G from the datasheet, 9.81, that is the value of gravity on the Earth's surface. So if you go too far away from the Earth's surface, then gravity changes. This formula, good for walking up the stairs, good for climbing a mountain, pretty good for going up in an aeroplane as well. If you're taking your rocket out, that's when this formula doesn't hold. So our two applications. We're going to look at a pendulum in motion, and we're going to look at a roller coaster. For the pendulum, it's displaced from its equilibrium position. The equilibrium position, if you just let that pendulum hang, the point right below where it hangs is the equilibrium position. So that's marked on the diagram. It's raised to a height h0 and then released from rest. Its kinetic energy at a certain point is going to be its loss in potential energy from maximum height. So if we look at the equilibrium position, for instance, that's where all of the potential energy it had up at the top, where it was released, is changed into kinetic energy. So up at the top, maximum potential, down at the bottom, maximum kinetic. When it gets through to that point in red, at I to H, it's got a mixture. It's got partly potential energy, partly kinetic energy. And the kinetic energy it's got is how much potential energy it's lost from maximum height. So we're saying that half mv squared equals mg delta h, the change in height, which in this case, h0 minus h. What about the roller coaster? If it's initially at rest at the top of the track and then accelerates down to speed v at the bottom after height drop h, its kinetic energy, half mv squared. Its potential energy, mg delta h. If those two things were equal, we would say that all of that potential energy has changed into kinetic energy. But what if it didn't? What if there were work being done overcoming friction and air resistance? Well, then we'd find the difference. What was the difference between what it had at the top and what it has at the bottom? That's going to be the amount of energy that's been used to overcome friction and air resistance. If we ignored it, they would be equal. So, describe the energy changes for a falling object. It starts off, it's got potential energy. That potential energy changes into kinetic energy as it goes down until it reaches a maximum speed, the terminal velocity. At that point, work has to be done to overcome friction to keep it at that speed. And that's it for today.